Alrighty, hello Year 11s. We are continuing with the topic of electricity and electric circuits today. So we're going through chapter 2.2. If memory serves. Yes. Anyway, we're starting on page 116. So the blue box on the top of the page shows everything that we need to learn about. So, first of all, energy is required to separate positive and negative charges, and this charge separation produces an electrical potential difference that can be used to drive currents in circuits. Alright, next, energy available to charges moving in an electrical circuit is measured using electrical potential difference, which is the voltage. This is defined as a change in potential energy per unit charge between two defined points in the circuit and is measured using a voltmeter. Next, electric current is carried by discrete charge carriers. Charge is conserved at all points in an electric circuit. Then electric current is the rate of flow of charge. An ammeter is used to measure the electric current at a point in a circuit. It is placed in series with the electrical component through which the current is to be measured. What you need to know how to do is describe how a voltmeter is used in an electric circuit, explain the purpose of measuring the potential difference in an electric circuit, describe how electrical safety is increased through the use of fuses, circuit breakers, and residual current devices, distinguish between electrical current and conventional current, and solve problems using I equals Q over T. And you're like, yes, what's Q over T? I'm going to tell you right now. So I equals Q over T is a formula, okay? I equals Q over T, where I is the current, Q is the charge, and T is, as always, time. Okay, now the unit for current is A, and for charge is C, and for time it is seconds. Okay, so we have our formula I equals Q divided by T. Yes, that's a T. I know this is a very badly drawn T, but it is a T. I is what's it called? Current. I equals current, which is given by the unit A. Q is charge, given by C, and T is time, given by S, being seconds. Okay, so the standard unit of current is the ampere, or amp for short. How many amps does something have? It's asking how much current does it produce. And for C is charge, coulombs, like we did last time. So an amp is defined as 1 coulomb per second. Alright, so in example 2.1, we have a very simple question there. So a battery supplies 156 Cs of charge to a smartphone in 60 seconds. Calculate the current flowing through the phone. So we have our charge, that's meant to be Q, which is equivalent to 156 C. We have our time, which is given to us as 60 seconds, and our I is unknown. Okay, 156 coulombs, 60 seconds, we don't know what the amps are. So let's calculate it. I is equivalent to Q over T. I equals 156 divided by 60, which is equal to 2.58. So 150 coulombs of charge to a smartphone in 60 seconds is equivalent to 2.5 amps. That's it. Alright, next we're looking at electric circuits. So when charge flows through a closed path and returns to a starting point, we refer to the closed path as an electric circuit. That's around. So we are considering direct current circuits, known as DC circuits, in which the current always flows in the same direction. Always goes one way. Doesn't go the other way, just the one. Okay. It is composed of a source of electrical potential difference, such as a battery or a wall outlet, a switch, conducting wires, and one or more electronic devices called components, which I'm sure all of you that are doing your Sparky training know exactly what I'm talking about. So if you don't, page 117, we have this lovely diagram here. We have the battery, we have the switch, we have the component, that's that thing in the center there, right there, the component, and then we have the connecting wire. So you have the switch to turn the battery on or off, or opens or closes the circuit, and then come to the wire, to the component, and then back through. Alright, so wires are made from metals such as copper, iron, and aluminium. Outer electrons of the metal atoms in the wire are weakly bound to the atomic nuclei, flowing freely. We went through this a bit last lesson. Metals are good conductors because they have loose electrons that flow through the metal nicely. Okay. Wires extend to the source of electric potential, blah, 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 blah. Okay. So you have the wire, the wire is metal, allows for electrons to flow through. A wire is then wrapped in an insulator, which doesn't allow the flow of electrons, so that way we are allowed to hold said wires and not die from an electric shock. Ready, next, measuring current. And yes, we will be able to do this at some point this term, using an ammeter. Ammeter. Anyway, electrical current in a point in a circuit is measured using an ammeter. Ammeter is placed in series with the electrical component through which the current is measured. Arrangement ensures that the current flowing in or out of the component is equal to the current flowing into or out of the ammeter, as shown in figure 2.18. In the circuit below, the ammeter measures the current flowing through the light bulb as 0.16 amps. Okay, so this diagram here. You have battery, ammeter, component. Electricity flows out of the battery into the ammeter. Yeah. And to the component and into the right. It's hard looking at these things upside down. Electron circuit with an ammeter. Because it's a red cord. Alright, so the battery supplying energy into the component and the ammeter measuring how much what the current coming out of the battery is that's going into the component. Alright. Electric current in nature, I'm sure you know. Lightning is electric current. Torpedo rays are fish that produce electricity. Also like electric eels, they also produce electricity. Pacemakers that we have in our heart, and the core of our Earth is molten iron, which produces a massive electric current, which is why we have north and south poles. They're not electric, they're magnetic, but they're related. Pretty sure we get to that later. If not, that's a year 12 subject, or it used to be a year 12 subject topic, sorry. We go into magnetism, which is good fun, but I don't think we do that, which is a little sad. That was fun. Okay, so next we have electric potential differences. So although electrons move freely in metal wires, they do not flow unless the wires are connected to a source of electric potential difference, such as a battery, a wall outlet, power supply generator, or a solar cell. Basically something that has a lot of potential to make that the electrons move from. From high potential. So energy moves from high potential to low potential, same as osmosis. Okay. Alright, so charges flow through the electric circuit from a high potential region to a low potential region. Close analogy is water flowing in a garden hose. If you hold the hose straight with both ends sticking up so the water doesn't flow out, the water doesn't go anywhere. If you raise one end higher and lower one end and turn the hose outwards, the water will flow from the top of the hose down to the bottom, because this is high potential energy and low potential energy, and the water goes from high potential to low potential. Okay? Source of potential difference performs in a similar function in an electric circuit. That is a lot of blah, 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 blah. That's a lot of theory. Okay. So there's a good figure on page 120 explaining a mechanical analog to a simple electric current, which is basically a water wheel and someone physically pouring water, going down a ramp, making the water wheel spin, and then pulling in more water to make the thing keep going. Okay. Alright, what we actually need to look at specifically is formula. There we go. Hello. So, we're looking at work or work done. So a battery or power supply is disconnected from a circuit and carries no current. The difference in electric potential between its terminals is called potential difference or voltage. So the symbol is given as delta capital V. Not lowercase v like we use for velocity, capital V, no arrow on the top. Okay, potential difference determines the amount of work in a battery or power supply does to move a certain amount of charge around a circuit. To be specific, the work done by a source of electric potential difference is the product of its potential difference and the quantity of charge moving between its two terminals. Thus, the work done is equal to the charge and potential energy. That's too many words. Okay, let's just look at the formula. Alright, so the formula for work done is work is capital W equals the change in volts times by charge. Okay, so W is work done. The unit, which is J or joules, as energy. Anything to do with energy, we use the unit of joules. That includes work done and kinetic energy, potential energy, all that. Joules. Joules. Delta V is volts. Oh, sorry, potential difference, which is in volts. Okay, and then Q, which is still the charge, which is C. Wow. Okay, so this is a formula. Work done is equal to the change in voltage times by the charge. W, work done, unit is in joules. Delta V is potential difference, unit is volt. Q is the charge, given as a C is coulombs. Okay, so if we were to use that, look at example 2.02, 1.5 volt battery supplies 26 coulombs of charge for a light bulb and a torch. Calculate the work done by the battery. Work done is a question mark. Delta V is 1.5 and our Q is 26C. So work done, delta V Q, which equals 1.5 times 26, which equates to 39 joules. Once again, do not forget to write your units at the end of your equation. Once you've solved it, slap the units on the end there. Don't forget your units. They are important. Alright. Potential differences. It is useful to measure potential difference. I'm not reading all of that. That's a lot of information. And then current flow. Alright. Current flow we'll let you read through. So this is on page 121. So when drawing a diagram of an electric circuit, an arrow is drawn in the direction of the current. By convention, electric currents point in the direction that the positive charge would flow in a circuit. So conventional current, positive flow. Okay? Positive flow for conventional current. To simplify this convention, we define two types of currents. First, called the conventional current, flow of positive charge, and the second is called the electron current, which is the flow of the electrons, which is in the opposite direction to the positive charge. Okay, so conventional currents flow from a positive to a negative, as a positive charge would flow from a region of high potential near the positive terminal to a region of low electric potential near the negative terminal. The electron current flows from a negative to a positive, and hence the conventional current and electron current arrows point in opposite directions. So figure 2.25, we have down here, we have our conventional current, positive, flowing in one direction. Then we have an electron current, negative, flowing in the opposite direction. And in a circuit, as shown here, this is the positive end, is going this way, go this way. We have the electron, the negative end, flowing the other way. So positive starts, positive, high potential, going to a low potential, and this is a negative potential going to a positive potential, the other end. Alrighty. Safety features in household electrical circuits. As you know, we have fuses, we have circuit breakers. Alright, now with a fuse, they use a very thin wire. Why? Because if there's an electrical short circuit, the fuse heats up and snaps, which cuts all power to the house, which means it happens in a quick enough period that you will not die from the electric shock. Okay? That's why you have a thin fuse, so if something catches on fire or something goes off and there's a zap, the thin wire melts, snaps, electric power, gone, dead. Alright, next you have a circuit breaker. Bimetallic strip. Contacts connected, bimetallic strip. There is current flows. If it separates, the current opens. Okay, so with a circuit breaker, there's something called a bimetallic strip. Okay? When it is cool, the contacts are connected and the current flows through the circuit. When a large current heats the strip, it bends enough to separate the contact and prevents the current flow. Unlike the fuse, which cannot be used after the wire melts, the circuit breaker can be reset when the bimetallic strip cools and returns to its original shape. Okay? Two different things. Shock hazard. There are some very good examples on these pages here explaining what happens with electric shocks. So we have, if you've ever seen power plugs here, you know that they have that one doesn't have a grounding strip. They usually have a grounding plug as well. Okay, so they have an earth pin. Okay, like this here, there are 3 pins. So, in, out, earth. It's an earthing plug for, that's a great question. It's connected directly to the ground when plugged into a 3-prong receptacle of a power outlet. In addition, the 3rd prong is wired to the outer enclosure of the electrical appliance. Suppose something goes wrong within the appliance and a high potential wire comes into contact with the outer enclosure. In that case, the resulting current flows to the 3rd prong rather than to the body of the person who happens to touch the case. Basically, if there's an electrical fault, the 3rd prong takes the shock, and instead of you getting electrocuted, the current goes back into the system. That's shown in the example on page 123, example 2.3. Okay, and same as a residual current device shown in figure 2.31, which is a hairdryer. And then there's a bunch of questions. Alrighty. Neat. And alright, so we're moving on to 2.2, which is resistance. So resistance or ohmic and non-ohmic components is defined by the ratio of potential difference across the component to the current in the component. The resistance of a conductor depends on its length, area of cross-section, temperature, and the type of material which is composed. Resistance is constant for ohmic resistors, Resistance is a constant for ohmic resistors which conform to Ohm's law. Ohm's law states that a current is directly proportional to the potential difference provided the temperature of the conductor remains constant. So your goal for the end of this chapter, of chapter 2.2, resistance, is to know how to solve problems involving R equals delta V over I. Okay? Literally just knowing how to use that formula. So, formula is R equals delta V over I, where R is resistance, delta V is potential difference, and I is current. Okay, resistance is in ohms, which is, the symbol is the Greek omega. The unit for potential difference is V, is volts, and the current is A, or amps. Okay. Formula. broken down. R, the resistance in ohms, with the should be omega. Delta V, which is potential difference, volts. V, I, current. A, amps. Okay. How do we use this? Example 2.03. Filament in a light bulb carries a current of 0.8 amps when connected to a 240 volt outlet. Calculate the resistance across the filament. Okay, so R is unknown, our voltage is 240, and our current is 0.8. Resistance is equal to change in potential difference of a current, which is equal to 240 divided by 0.8, which is equivalent to 300 ohms. Okay, that right there. Simple as that. Resistance unknown, change in voltage or potential difference we know, current we know, plug what we know into our equation, get the answer. Ta-da! Simple as that. Right. Then we have a section which talks about conductors, ohmic versus non-ohmic conductors. So materials that are well approximated by Ohm's law are said to be ohmic conductors, as they show a simple linear relationship between current through a conductor and the potential difference between its ends. Figures that do not well approximate are called non-ohmic conductors. Non-ohmic conductors have a more complex relationship between potential difference and current. A graph of potential difference for a non-ohmic material is nonlinear, indicating the material does not have a constant resistance. The resistance of a non-ohmic conductor is approximated for a given potential using the graph as shown in figure 2.34. Examples of non-ohmic conductors include light-emitting diodes, incandescent light bulbs, thermistors? Wow. Thermistors and semiconductors. Yeah, two different graphs there. Right, next looking at resistivity. The resistivity of a conductor is dependent on several factors, including a type of material which is composed. For example, a wire made of copper has a lower resistance than a wire of the same length and diameter made of iron. The quantity that characterizes the resistance of any given material is its resistivity, given by Rho. Rho, I guess it would be in English. It's this symbol here. Okay? Rho. And you're like, Miss, that doesn't look like a character. If you go to page 131 in your textbooks, it's right there. Okay? It's the Greek letter Rho. Okay? And there's also a table there of resistivities. So copper has a very low resistivity, and glass has a very high resistivity. I hate that word. Okay? Resistance of a wire also depends on its length and cross-sectional area. So we have a formula for that. Okay? What is a formula, you may ask? Resistance is equivalent to Rho L over capital A. Okay? So let's break that down. R equals resistance. Rho is resistivity. Resistivity. L is length and A is cross-sectional area. Okay, resistance is ohms. Resistivity is ohms per meter. Length is meter, and cross-sectional area is meter squared. That's a lot of meters. Anyway, so formula. Breakdown of the formula. R, resistance, ohms. Rho, resistivity, ohms per meter. Length, L, length, meters. A, area, cross-sectional area, given by meters squared. Okay, so to use the formula on page 132, example 2.04. An electric shower is connected to the mains to the main supply by a copper cable 20 meters long. 2 conductors lay inside. Each cable have a cross-sectional area of 4 times 10 to the negative 6 meters squared. Calculate each conductor's resistance if the resistivity of copper is 1.7 times 8 to the negative ohms per meter. Okay, so R is unknown, Rho is 1.7 times 10 to the negative 8. L is 20 meters, and area is 4 times 10 to the negative 6 meters squared. Make sure you're all working in the same units. Something is in meters, make sure that all your things are in meters. Okay? Alright, now we have our equation. We plug in our values. Is 1.7 times 10 to the negative 8. Put that in brackets. Times by 20 divided by 4 times 10 to the negative 6. Yes, it's equates. So you should have this as a formula. We plug that formula in, plugged our numbers into a formula. So 1.7 times 10 to the negative 8 times by 20 divided by 4 times 10 to the negative 6. Make sure you put the brackets in when you stick it in your calculator so that it knows what it's doing correctly. Okay, and that should equate to 0.085 ohms. Okay, that's it. That's it. That's how you use it. Done. Easy. Simple. Okay. Now, while you may not get the resistivities on your cheat sheet, on your formula sheet, you will get them in a question. It may also be on your formula sheet, but as far as I'm aware, it's not. Okay? Alright. Ready, resistors. That is an entire page of theory for you to read, and then it's just a bunch of questions until we get to 2.3. And that is where we will leave it for today, year 11s. Alright. That's it. Actually, before you... Actually, no, we will send it there. We'll end it there. Alright. Bye!